Oh, okay. I'm recording again. Okay, thank you. Okay, so we're back here. So this is A21, this is A22, this is A23, this is A31, A32, and A33. Okay, so these are all the entries of this matrix. So the entry A11, right, is this entry right here. So that's our entry. And so the minor of this entry, the minor of entry A11, is denoted by this capital M11. And so in order to find this entry, what you do is you cross out the first row and the first column of A. Okay, so you see this thing here. All the letters I'm going to bold, I'm getting rid of. So I'm getting rid of this number, and this number. And I'm also getting rid of this and this. Everything in the first and third rows. Because the 1 here denotes first row. So I'm just going to get rid of it. And the first column, I'm going to get rid of the first column. So I'm left with is now what's left? 5, 6, 4, 8, right? But I'm going to take the determinants of the resulting submatrix by getting rid of those rows and columns. So what am I left with? I'm left with 5, 6, 4, 8. I got rid of the first row because of the first index is a 1. And I got rid of the first column because the second index is a 1. And that leaves me with 5, 6, 4, 8. And so the minor of entry A11 is the determinant of the submatrix after removing those rows at row and column. And well, this is the determinant of a 2x2 matrix. And remember, determinants, we use this notation, this vertical line notation, as an alternate notation for the determinant. And so okay, so this is just another notation for determinant of a matrix. Okay, so this is the determinant of that matrix. And so that's just 5. That's 5 times 8 minus 6 times 4. Because you multiply on diagonal, right? If you want to find, I'm going to try to rely less on this. If you have the entries, oh, okay. This was our original matrix. The entries were 3, 1, -4, 2, 5, 6. Okay, and so we're finding the minor of entry A11, right? To find the goal is to find the minor of entry A11, right? And that so the notation for it is capital M sub 11. And so what you do is, again, the first one gets rid of the first row. And now the second one gets rid of the first column. And so you're left with that submatrix. And so capital M sub 11 is just the determinant of the submatrix after you got rid of that red row and green column. So it's the determinant of 5, 6, 4, 8. And remember, when you find the determinant of a 2x2 matrix, it's like going in this direction than this one. I'm not getting rid of them here. These are representing the multiplication involved. It's illustrating 5 times 8 minus 6 times 4. Okay, well, that's equal to 40 minus 24, which is 16. So capital M sub 11, the minor of entry A sub 11 is 16. That's the answer to what the minor of entry A11 is. Okay, so that's the minor of entry A11 at 16. Okay, so this is just 40 minus 24, which is equal to 16. And so that's the minor of entry A11. And so we can find the minor of each entry in the same way. So M sub 12 is just, if you continue these calculations, you would just get, I guess I could do this really fast. So you have M sub 12, you have M sub 13, you have M sub 21, you have M sub 22, you have M sub 23, you have M sub 31, you have M sub 32, you have M sub 33. Okay, so you have the minors of each entry and they're equal to the determinants. Okay, so you have a determinant here, you have a determinant here, roll determinants. Okay, and so if you get rid of the first, this is M12 is you get rid of the first row and second column. So you get rid of the first row and second column, you're left with 2, 6, 1, 8. See that? First, get rid of the first row because of the 1, and get rid of the second column because of the 2. 2, 6, 1, 8. And so that's equal to 16 minus 6, which is 10. And then M13, you get 2, 5, 1, 4. 2, 5, 1, 4. And so that's 8 minus 5, which is 3. And then 2, 1, second row, you get rid of the second row and first column, you get 1, negative 4, 4, 8. You have 1, negative 4, 4, 8. And then cross multiply, you get 8 minus negative 16, which is 24. And then M22, second row, second column, 3, negative 4, 1, 8. 3, negative 4, 1, 8. 24 minus negative 4 is 28. M sub 2, 3. You get 3, 1, 1, 4. 3, 1, 1, 4. This is 12 minus 1, which is 11. And then 3, 1. You get 3, 1. 1, negative 4, 5, 6. 1, negative 4, 5, 6. And so that's equal to 6 minus negative 20. That's 26. And then this one, 3, 2, third row, second column, 3, negative 4, 2, 6. 3, negative 4, 2, 6. And so that's equal to 18 minus negative 8, which is 26. And then 3, 3, third row, third column, 3, 1, 2, 5. This is 3, 1, 2, 5. And you cross them out, you get 15 minus 2, which is 13. Okay, so these are all of the minors of each of those entries. So there's 9 entries, so there's correspondingly 9 minors. Okay, so the cofactor of the entry A11 is, well, so the cofactor of A11 is notated C11, and it's equal to negative 1 raised to the 1 plus 1 power, where the 1s are coming from the indices. So if you're adding the indices as an exponent of negative 1, and you're multiplying it by M sub 1, 1. Okay, so C11 is just negative 1 raised to the sum of these numbers, 1 plus 1, negative 1 to that sum, times the corresponding capital M sub 1, 1. And so negative 1, that's negative 1 squared, which is 1. This is 1 times what M sub 1, 1 is, which is 16. This is 1 times 16, which is 16. All you're doing is you're taking each of these minor entries and multiplying them either by negative 1 or positive 1, depending on the power of negative 1. If you take C sub 1, 2, this is equal to negative 1 raised to the 1 plus 2 power, because you're taking the sum of the indices down here, 1 plus 2, and then you're multiplying it correspondingly by M sub 1, 2 for C sub 1, 2. Now that's negative 1 cubed, which is negative 1. And so you're taking the negative 1 of M sub 1, 2, which is 10. Okay, and so it's -1 times 10, and that's equal to -10. Now, as a shortcut, what you can see is that if you're, I need to go to the whiteboard for a second. If you look at the original matrix, here, C sub 1, 1 had a -1 squared, which is positive, and C sub 1, 2 had a -1 there, which is negative. You get a checkerboard pattern where the value of -1, the sum of the indices, is equal to plus or minus 1 according to the pluses and minuses in this check diagram. So -1 raised to the I plus j is equal to 1 for all the entries with a plus. That's equal to -1 for all the entries with a minus sign. Okay, so all the entries in which there's a plus sign means the value of -1 to the I plus j is 1. And all the places with a minus sign, the value is -1. And so what that means is that the coefficients are going to be 1, -1, 1, -1, 1, -1, 1, -1, 1. And at the top left, there's always a plus sign or a 1. So you always start at the top left with a plus sign or a 1, and then everything else gets filled in by just alternating it as you go right, down, up, or left, not diagonally. Diagonally doesn't matter. Okay, and so you just get that checkerboard pattern. And so what that means then is that originally, when you found the minors of each of these entries, right? Right. So if you looked at, if you looked at the matrix of minors, meaning here is M11, here is M12, here is M13, here is M21, M22, M23. This is M31, M32, and M33. This would be the matrix of minor entries, right? If you look correspondingly at the matrix of cofactors, though actually, first I'm going to fill this in. So the minors we have here are 16, 10, 3, 16, 10, 3. The second row is 24, 28, 11. 24, 28, 11. And then the third row is 26, 26, 13. This is 26, 26, 13. So those are the matrix of minor entries. And then if you look correspondingly at the matrix of cofactor entries, you have C11, C12, C13. You have C21, C22, and C23. You have C31, C32, and C33. This is the matrix of cofactor entries. Well, the only difference between the matrix of cofactor entries and the matrix of minor entries is that you're taking plus or minus 1 times each one. So this is 16, this is 28, this is 3, this is 26, and this is 13. All of these are, it's not that they're positive or negative, they're just the same as the minor entries. All those are the same. And then the other ones are the negatives of what they are. So if this was a -24, this would be a +24, but it's a -24. And then this is a -11, and this is a -26. And so these are the corresponding matrix of cofactor entries. Okay, so now we found the cofactor of every entry. Okay. Okay, so let's go back to let's go back to this problem in a little bit. Okay, so we have to talk about a few more things, and then we can finish this problem with that information. Okay, the determinant of A can be determined / expressed in terms of cofactors in these 4 ways. Okay, so here, here capital A is a 2x2 matrix. Okay, so we are now not thinking about this problem at the moment, and we're just talking about something else. Here A is a 2x2 matrix. So determinant of a 2x2 matrix can be determined / expressed in terms of cofactors in these 4 ways. If you have the determinant of a matrix capital A, well, that's first equal to, just using some other notation, right? We're finding the determinant of this matrix here. So you can write this determinant as A11. So keep in mind, we already know this is A11 times A22 minus A12 times A21, right? That's from the way we multiply, right? AD minus BC. Well, this is equal to A11 C11 plus A12 C12. And for this, I want you to look at the first row. Okay. For that, I want you to look at the first row and notice that we're taking the entries in the first row, multiplying them by their corresponding cofactors, and then adding the products. So it's A11 times C11 plus A12 times C12. It turns out this expression is equal to this expression. Okay. Now, if you look at the second row, then you also get that the determinant is equal to A21 times C21 plus A22 times C22. And this is now looking at again, the second row. So looking at the second row, you can take each entry in the second row, multiply them by their corresponding cofactor, and add the products. And you still get the determinant if you do that of a 2x2 matrix. In the first column, if you take the entries in the first column, multiply them by their corresponding cofactors, and add the products, then you still get the determinant. So in the first column, you just take the entries in the first column, multiply them by their corresponding cofactors, and add the products, and you get the determinant of A. You get A11 A22 minus A12 A21. And lastly, you can go into the second column. And so if you're in the second column, you take the entries, each entry in the second column, and multiply them by their corresponding cofactor and add the products. And then you still get the determinant that way. Okay, so if you take each entry in the second column, multiply them by their corresponding cofactor, and add the products, you get the expression A11 A22 minus A12 A21, which is the determinant of that matrix A. And so you can go along row 1, row 2, or column 1 or column 2, do this thing, and you get the determinant all 4 times. Okay, each of the 4 expressions above are called a cofactor expansion of the determinant of A. Okay, it's the way of expressing the determinant of a matrix using cofactors. Okay, each came from the same row or the same column of A. So meaning the expressions, everything in an expression came from the same row or same column. Okay, so this is a theorem. It's theorem 2.1 1.1 in the book, it says if capital A is an n by n matrix, then regardless of which row or column of A is chosen, number obtained by multiplying the entries in that row or column by the corresponding cofactors and adding the resulting products is always the same. So if you have an n by n matrix, then regardless of which row or column of that matrix is chosen, the number obtained by taking each entry in that row or column, multiplying it by its corresponding cofactor, and then adding the products, that entry is always the same. And we see that in this example. We did this in row 1, row 2, row 3, and row 4. I can show you that all 4 of these expressions equal this expression, which is the determinant of a 2 by 2 matrix by definition. Okay, but they're always the same, and it's proved in this theorem. And so this expression that you get, that's the same regardless of the row or column you choose, that's the determinant of a matrix A. And since this number is always the same, we get a well-defined definition of a determinant, meaning no matter which row or column you choose, the value is always the same as the determinant of that matrix. Okay, so definition. If capital A is an n by n matrix, a square matrix, we only care about n by n matrices here. If A is an n by n matrix, then the number obtained by multiplying the entries in any row or column of A by the corresponding cofactors and adding the resulting products is called the determinant of A. And the same and the sums themselves are called cofactor expansions of A. So this defines the determinant of a matrix A and the cofactor expansion of the matrix A. Okay, so that is another way to write this is if you take the determinant of a given matrix A is equal to a cofactor expansion along any column J. So below this, what I'm writing is the cofactor expansion along column J, where J is arbitrary. It's an arbitrary column, J. And so this is equal to A sub 1J, C sub 1J. That means in column J, it's the entry in the first row of that matrix in column J. And so the entry is A1J multiplied by the corresponding C1J. Then as you move along column J, so let me go to the whiteboard. This is kind of fast. Okay, so if you have a matrix, right, and you look at column J, this is column J. Then the entries in column J would be the first row would be A1J. The second row would be A2J. The third row would be A3J. And then dot, dot, dot. The nth row, because it's n by n matrix, be ANJ. And so you'd be taking the entries in the jth column, multiply them by their corresponding cofactors, and then add the products. Okay, so you're just selecting column J of a matrix, and you're taking each entry in that column, and you're multiplying it by its corresponding cofactor and adding the products. So that's what's happening here. Then you A2J times C2J plus A3J C3J plus dot, 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 plus the last entry in that column, A and J, C and J. Okay, so that's the determinant of A for an arbitrary column J. So for any J, where J represents the column of your matrix, if you plug in that value of J into this entire expression, you get an expression for the cofactor expansion along column J, which equals the determinant of that matrix A. Now you can also find a determinant along any row, because the quantity from our previous theorem 2.1.1, it says that value has to be the same. So here I'm going to give a general expression for the cofactor expansion along row I. Okay, and so I want all this together. So I'm going to put this here, just because it's one line. And so now I'm going to give an expression for a row. So just give me a little more test. This is column J. And now if you look at row I, if you have a matrix and you look at row I, then for row I, let's say you look at the ith row. So here's going to be the ith row. This is the ith row. Now for the ith row, you have the entry in the first column, so it's AI1. For the entry in the second column, you have AI2. So the entry in the third column, you have AI3, ... The last entry in the ith row is AIN, because it's in the nth column. And so now this is the ith row of your n by n matrix. AI1, AI2, AI3, ... AIN. You take each of those entries, multiply them by their corresponding cofactors, add the products, and that's also the same value as the determinant of the matrix. And so you have AI1, CI1, plus AI2, CI2, plus AI3, CI3, plus ... plus AIN, CIN. And so that represents the cofactor expansion along row I for any I. So if you only consider I's where row I is a row of your matrix. If it's a 3 by 3, you can't take row 10, right? So take an appropriate value for I, plug that same value of I for the entire thing, and that is a cofactor expansion along that row, which equals the determinant of your matrix. And so this gives a way of finding the determinant of a matrix in terms of cofactors along any row or any column. And so very quickly, to just another minute, a few minutes, for this example, we have the cofactor entries for every entry of the matrix. And so from our work below the black line, we can find the determinant of the matrix in this problem. Okay, so the original matrix A was this matrix. And so now we just want to find the cofactor expansion along any row or any column. And so the determinant of this matrix in the problem is equal to, well, let's go along the first row. The first row is entries 3, 1, -4. So we want to take each entry. We have entries 3. We have entry, is it 4? We have 3, 3, 1, -4. We have 3, 1, -4. So right, see, those are the entries 3, 1, -4. And then take the cofactors of those entries. So the cofactor for this entry was 16. The cofactor for this entry is -10. And the cofactor for this entry is 3. And so you just add the products of entries times their cofactors in any row or any column. So I chose the first row. So here, it shows the cofactor expansion along the first row of the matrix. Okay, and so now when you find the value for the first row, you get 48 minus 10 minus 12. And so 48 minus 10 minus 12 is 26. And so the determinant of that matrix is 26. And that's the answer. Okay. Okay, so we're ending. There's only 3 minutes. Okay, so that's the determinant of the matrix. And so now I've given you a definition of determinant, and I've shown you how to compute the determinant for this row. You could do it for any row, any column. Okay, so let me just save the whiteboard. Class is now done. I'll see all of you